right, so we are learning about a famous mathematician today named L'Hopital. L'Hopital was historically the first mathematician to come up with this theory in mathematics, and there became a feud between L'Hopital and Bernoulli, and if you continue on in your mathematical studies, you'll actually learn about both of these guys. They did a lot of cool things for mathematics back in the day. And these two got into a feud about what was happening in the math world. We're going to take a pause. So back to our famous mathematicians and their feud. So back in that time, obviously, communication was not as speedy as it is today. So simultaneously, both of these guys are discovering this rule for limits, and they're discovering it in two different parts of the world. So they had to go based on textbook letters back and forth the family to try to figure out who became the actual creator of our rule, and L'Hopital was our winner, or victor. So L'Hopital is a way in which we can analyze the behavior of a function and find our limit much more easily. So L'Hopital's allows us to find the behavior of a function much more easily than trying to actually take the limit. So we're going to talk about the indeterminate form today. And we've talked about the indeterminate form a little bit in the past. So you're now going to be able to take this limit. And you know that if you plug in 1, the limit as x approaches 1 of natural log of 1 is 0. 1 minus 1 is 0. So today we're going to learn a way to take a limit when you get 0 divided by 0. So we have the indeterminate form. So here, if you try to take the limit as x approaches 2, you plug in 2, you get 2 squared is 4. 4 minus 4 is 0, and so on and so forth. So in your packet, I gave you graphs so you could sort of see what we're going to look at indeterminately, while we also look at it algebraically. So those graphs on your handout, we will come back and reference, but I like them to be there on that front just so you have them nice and easy. 0 divided by 0 is considered what we call the indeterminate form. 0 divided by 0 is the indeterminate form. So in the past, what you would do if you had 0 divided by 0 is algebraically simplify that. So in the past, if you got that question, you would say, okay, well, the top is a difference of squares. So you'd factor it as x minus 2, x plus 2. And then we'd say, okay, well, there is a removable discontinuity at x minus 2. So we can remove that discontinuity. And that's really equal to the limit as x approaches 2 of x plus 2, which is really like 2 plus 2 or 4. So where that removable discontinuity occurred, my graph from the left and the right was approaching 4. So what that means is graphically when x is approaching 2, there is a hole at 4. So directly substituting gave you 0 over 0. Factoring and canceling gives you 4. if you look at this on a graphing calculator, which is what we're going to do on that back of the next page, this graphs originally as a quadratic divided by a line. So their point of intersection is at that removable part. So what we're doing essentially mathematically, which is what those guys calculated, is looking at the limit of the ratio of the numerator, comparing it to the limit of the ratio of the denominator. So you're comparing the numerator to the denominator at that point 2. So essentially we are looking at the slope or the limit ratio at 2, comparing the numerator to the denominator. So L'Hopital says that if that comparison gives me 0 over 0, instead of having to factor and cancel, I can derive. So he said, instead of factoring and canceling, let's compare the slopes at those 2 points. So he said, let's compare what happens if you look at the slope of those 2 points at that identical time. So we're going to compare the derivative of the top to the derivative of the bottom. So L'Hopital's rule is to compare the derivative of the top to the derivative of the bottom, which is really a comparison of their slopes. It's derivative of the top to derivative of the bottom, which is a comparison of their slopes. So let's compare their slopes. The slopes of the numerator is 2x. The slope of the denominator is 1. So the numerator slope compared to the denominator slope is 2x over 1. Looking at your limit, oh, we get that same 4 I just got. So the slope of the top over the slope of the bottom is the same. As the limit using factor and cancel. So the new rule for L'Hopital's is that if you get 0 over 0, you can take the derivative of the top over the derivative of the denominator. No more factor and cancel. If the limit as x approaches a, if f of x is the indeterminate, which means that you get the limit of the top equaling 0 and the limit of the bottom equaling 0, or that the top goes to infinity and the bottom goes to infinity, then that's equal to the limit as x approaches 0, where you take the derivative of the top and divide it by the derivative of the denominator. And we can do this process infinitely until we no longer get 0 over 0. So L'Hopital's rule again says that if the limit as x approaches a of f of x over g of x is Do you know who it was? Okay. It was so loud, I actually thought it was my iPad through like the Apple TV for a second, but I was like, I don't know who'd be calling my iPad. All right, questions, comments, concerns? it should be a pretty easy, like, oh, why didn't you teach me this back in September type thing. But the idea is that you have to actually understand how derivatives work. You have to actually understand how the indeterminate form works. And we need to be able to simplify any and all types of derivatives to apply this rule. So let's look at some examples. We have that very, very original one again. So you know that you get 0 over 0 through direct substitution. So now and if you do this on an open-ended free response question, you have to say by L prime H, by L'Hopital, the limit as x approaches a of the derivative of the top over the derivative of the bottom, where a is 2, becomes 4. So you show the 0 over 0, then you say by L'Hopital, and you show the limit with the derivative of the numerator over derivative of the denominator and find your value. We can do this by working backwards. So we can confirm this algebraically by working backwards. So again, I know how important it is sometimes to understand how it works. So let's take, for example, the definition of the derivative and looking at a limit. So if you have the limit as x approaches 1 for the natural log of x over x minus 1. So again, going back to that first problem we referenced to start this unit, if you plug in 1, you get 0 over 0. So we can work backwards to understand how this works, because think about the definition of the natural log. Its derivative is 1 over x. The derivative of x minus 1 is 1. So you get 1 over x over 1, which gives you 1 over 1 over 1, which gives you 1. So going back to that, again, beginning initial example. The next problem is the graph that's on that front page, just with a negative applied a little differently. So, again, this is supposed to be sort of that easy understanding. So on that front page, you have cosine x minus 1 over x squared minus x. That is the same as this, but the x is distributed and the negative is pulled. So if you plug in 0 through direct substitution, cosine of 0 is 1. So you get 0 over 0. So then you say, by L'Hopital, the limit as x approaches 0, the derivative of 1 is 0. The derivative of negative cosine is positive sine. If you ignored the negative and you just take the derivative of cosine, you'd get negative sine. So you'd get a negative times a negative, which is a positive. Derivative of x is 1. Derivative of x squared is 2x. So this is the limit as x approaches 0 of sine x over 1 plus 2x. So the limit as x approaches 0 of sine 0 over 1 plus 2 times 0. Well, sine of 0 is 0, but 1 plus 0 is 1. This is not the indeterminate form. This is an answer of 0 because you have 0 up top divided by 1. So that is allowed in the mathematical world. So that's not an indeterminate. Once you take that limit, that is the actual answer. So there is a difference between 0 divided by 1 and 0 divided by 0. Okay? So once again, this would have been a problem back in the day that you had to use your complex conjugate. Because when you plugged in 0, you would have had the square root of 1 plus 0 minus 1 minus 0 over 2 all over 0 squared. Square root of 1 is 1. 1 minus 1 is 0. 0 minus 0 is 0 over 0. So again, on the AP exam, in order to use L'Hopital's, you have to show 0 over 0. Now, if it's multiple choice, you obviously do not. But if it's in an open-ended, you do. And then you have to say by L'Hopital's. And you take the derivative of each. Derivative of 1 of square root 1 plus x is 1/2. 1 plus x to the negative 1/2. Derivative of the inside in this case is 1. Derivative of 1 is 0. Derivative of negative 1/2 x is negative 1/2. And again, you're not cleaning it up or simplifying it with the denominator. You're essentially taking the limit of each separate. So it's the limit of the top over the limit of the bottom. And then once you have your derivatives of each, you plug them in. And I get 0 over 0 again. If you get the indeterminate form again, you do L'Hopital's again. So if I get my derivatives and I get 0 over 0, then you do L'Hopital's again. So you take the derivative of the top and the derivative of denominator again. So it's 1/2 times negative 1/2. 1 plus x, now to the negative 3/2 times 1. Derivative of 1/2 is 0. And derivative of 2x is 2. So again, you're looking at the limit of the top and bottom separate. half times a negative a half is negative a half. 1 to anything is 1. So we get negative 1/4 over 2. And negative 1/4 divided by 2 is really negative 1/8. Do you want your break with the rest of the world so you can see people, or do you want your break after all of them? There's only 3 examples left. Okay. All right, so finishing through our examples, there is a slightly different or varying form of the indeterminate. So the indeterminate form can also appear as infinity over infinity. It can appear as infinity times 0, infinity minus infinity, 1 to the infinity, 0 to the 0, etc. If you get any of the parts in blue, you have to change your limit to look like a fraction. If you get anything in blue up on that screen, you have to change your limit to be a fraction because L'Hopital's applies to a fraction. So we're just going to look at manipulating the next 3 examples so that they become fractions. So the rule is still the same. The application is still the same. We're just going to rewrite or transform the equation to fit the bill of what is required. So we have the limit as x goes to infinity. So if I have a limit going to infinity, I'm probably going to see the indeterminate form infinity over infinity. But what I notice about this problem is that there is no fractional aspect to it. So the minute you see this problem, at first you're not thinking L'Hopital's because you're not seeing a fraction. So if you plug in just the infinities to start, you'd get infinity times sine of 1 over infinity. Well, the sine of 1 over infinity, think about 1 over anything really big. That's really small. So the sine of 1 over infinity is kind of like the sine of 0, which is 0. So this is kind of like infinity times 0, which is indeterminate. So what we're going to do is rewrite that as a fraction. So in order to rewrite it as the fraction, that sine of 1 over x is locked together. And we're going to make that my numerator. But if you think about x, I can transform that to be 1 over x. And that's still equivalent because 1 over x, if you multiply by the reciprocal of that to get your common denominator, you end up with x. So we're going to take x and we're going to keep it easy. We're going to rewrite x as 1 over x. So the 1 is part of that sine x part here. And then the 1 over x is going to put it down there. So there's my 1 over x. Now, when you look at this as a limit, you get the sine of 0, which is 0. And you get 1 over infinity, which is also 0. because 1 over infinity behaves like 0 because it's like 1 over the infinitely longest thing ever, which makes it 0. So now we have a fraction. We have 0 over 0, so we do L'Hopital's. So you have the derivative of sine 1 over x, which is cosine 1 over x. Don't forget your chain rule says you have to multiply by the derivative of 1 over x, which is negative 1 over x squared, because 1 over x is really like x to the negative 1. So that's negative 1, x to the negative 2, which rewrites as negative 1 over x squared over, again, x to the negative 1, which is like negative 1, x to the negative 2. Now, do not fall for the trap. We're not going to cancel and simplify. We're going to plug in because you're looking at each of those limits of the top and bottom separately. So that 1 over x squared could kind of get written out in front of our limit in a way. But if you think about the fact that that is behaving as an asymptote, where does the cosine as x goes to infinity, which is like the cosine of 0, go? To 1. Perfect. So this limit is going to 1 because of the horizontal asymptote of cosine of 1 over x being at infinity going to 1. And then the nature of the other two parts of those limits sort of becoming canceled over each other. So they would also have vertical or horizontal asymptotes at 1. So L'Hopital's rule sort of brings everything back together. So in the case of a natural log, we know that 1 over the natural log of 1 would be like 1 over 0. So you get 1 over 0 minus 1 over 0, which is really kind of like saying, remember, 1 over 0 is like infinity. So that gives the indeterminate form infinity minus infinity. So 1 over infinity is like 0. 1 over 0 is like infinity. So let's get a common denominator, right? If we're subtracting fractions normally, we get a common denominator. So if I told you 3/4 minus 3/5, you'd get a common denominator. So we're going to do that for this problem. So you're just going to cross multiply the x minus 1 and the natural logs. And when you get a common denominator, you get 0 over 0. And creating a common denominator, I get a fraction. Derivative of x is 1. Derivative of negative 1 is 0. Derivative of natural log of x is 1 over x. And then be cautious and aware. The derivative of the denominator is a product rule. First, second. So you have to do the product rule because it's a function times a function. So the product rule says the first times derivative of the second plus the second times derivative of the first plug in your limit values. One minus 1 is 0. Natural log of 1 is 0. Plus 1 minus 1, which is 0, and 0 plus 0 is 0, and you're kind of angry because you got the indeterminate form again. So you L'Hopital it. Derivative of 1 is 0. Derivative of negative 1 over x squared. Well, that's kind of like negative x to the negative 1. So a negative times a negative became a positive. Take 1 away and you get x squared. So you get positive 1 over x squared. Just kidding, I tried to move so you could see better, but I can't move it. And then if you take derivative of the bottom, derivative of natural log of x is 1 over x. And here, well, that's really like x over x minus 1 over x, because you can take the bottom and resplit it. So x over x is 1, which is 0, and 1 over x is a positive 1 over x squared. Taking your limits separately, you get 1 over 1. 1 over 1 plus 1 over 1, which is 1 over 2. So your limit is a half. There will be nothing like example 6 this year because they got rid of the ln natural log. So you can cross off 6. So again, you guys have a couple things that got eliminated from your exam. So go ahead and take your break. When you come back, I have today's packet and tomorrow's packet with the problems that we'll be looking at to practice L'Hopitals and still practicing U-sub and fundamental. All of that will be due Wednesday at 8:30.